The moment the words black hole enter a conversation, something visceral happens. Images rush in uninvited, stars shredded like paper, planets stretched into glowing spaghetti, entire galaxies vanishing into darkness. Movies show them as cosmic vacuum cleaners, endlessly hungry, drifting through space with one goal: consume everything. It feels reasonable, almost intuitive, to wonder whether Earth might someday be next. This fear didn't come from nowhere. Black holes sit at the edge of what physics can describe, where familiar rules seem to break down. When science admits uncertainty, imagination rushes to fill the gap. Headlines amplify the drama, science fiction leans into terror, and suddenly, a distant astrophysical object becomes an existential threat. The contrast between what we know and what we fear creates a perfect breeding ground for anxiety. But here's the first crack in that fear-based story. If black holes are as dangerous as popular culture suggests, the universe should already look very different. Galaxies would be shredded chaos, stars would rarely survive, and stable planetary systems like ours would be almost impossible. Yet the night sky tells a calmer story. Order exists. Structure persists. Earth has orbited the sun for billions of years without being pulled into oblivion. That contradiction is where curiosity should replace panic. Fear thrives on vagueness, but science thrives on specificity. How dangerous something is depends not on how extreme it sounds, but on how it behaves. A shark is terrifying in the ocean, irrelevant in a desert. A volcano is catastrophic nearby, harmless across the planet. Context matters, distance matters, physics matters, physics matters. Black holes feel uniquely threatening because they challenge our intuition about gravity. We are used to forces that weaken with distance, experiences that feel predictable. Black holes, with their warped space and invisible boundaries, feel like rule breakers. But this is a psychological reaction, not a scientific conclusion. Our brains are wired to treat the unknown as dangerous, especially when it cannot be seen or directly experienced. There's also a deeper, quieter fear at play. All symbolize loss of control. Quieter fear that once something crosses a certain boundary, there is no return, no information, no rescue. That idea unsettles us because it mirrors something profoundly human, the discomfort with finality. We project that unease outward, turning a physical phenomenon into a cosmic villain. So before asking whether black holes are dangerous to Earth, a better question comes first. Are we afraid of black holes because of what they do, or because of what they represent? This distinction matters. One is a problem of astrophysics, governed by equations and observations. The other is a problem of perception, shaped by stories, metaphors, and emotion. This section is not here to dismiss fear outright. Fear is a useful signal. It tells us where our understanding ends, but it is also a starting point, not a conclusion. By recognizing how the fear of black holes is constructed, we clear space for something more powerful than reassurance, understanding. And once understanding enters the picture, the universe often becomes less terrifying, but far more interesting. In the sections ahead, that understanding will be built step by step, replacing cinematic destruction with measurable reality, not by draining the wonder from black holes, but by sharpening it. Because the truth is rarely that the universe is out to get us. More often it is indifferent, governed by consistent rules that only feel threatening when misunderstood. Once those rules are visible, fear loses its grip and curiosity takes over. That shift, from dread to insight, is where real science begins, and where the story truly starts for anyone willing to look. To understand whether black holes are dangerous, the fear has to be replaced with clarity. That means starting with what a black hole actually is, not what it feels like it should be. At its core, a black hole is not a cosmic predator roaming the universe. It is a consequence of gravity doing exactly what gravity always does, only pushed to an extreme limit. A black hole forms when a massive star reaches the end of its life. For most of its existence, a star survives through balance. Gravity pulls matter inward, while energy from nuclear fusion pushes outward. When the fuel runs out, that outward pressure collapses. Gravity wins. The star's core compresses so intensely that space itself bends beyond a critical point. That point is what we call a black hole. Nothing magical happens at that moment. No new force appears. No cosmic vacuum switch turns on. The same gravity that once held the star together now acts on a much smaller, denser region. The reason black holes feel so exotic is not because they break the laws of physics, but because they follow them so precisely that our intuition struggles to keep up. One common misconception is that black holes suck things in. Suction implies active pulling, like a vacuum cleaner dragging objects toward it. Black holes don't work that way. They attract matter in the same way Earth attracts you, or the sun holds planets in orbit. The difference is strength, not behavior. If the sun were magically replaced by a black hole of the same mass, Earth would continue orbiting almost exactly as it does now. The defining feature of a black hole is the event horizon. This is not a physical surface but a boundary in space. Cross it, and escape becomes impossible, not because something grabs you, but because the geometry of space tilts inward so steeply that every possible path leads deeper inside. From the outside, however, this boundary is invisible and passive. Objects do not suddenly accelerate toward it unless they are already extremely close. This is where contrast becomes essential. Popular stories treat black holes as endlessly hungry entities, but in reality, they are astonishingly small compared to the space around them. Even supermassive black holes, millions or billions of times heavier than the Sun, occupy a tiny region at the centers of galaxies. Most of the galaxy remains calm, stable, and unaffected at everyday distances. Black holes also obey a simple rule that often surprises people: distance dominates danger. Gravity weakens rapidly with space. The same black hole that would destroy you up close would be completely harmless far away. This is not a special exception for black holes. It is how gravity works everywhere in the universe. When stripped of metaphor and fear, a black hole becomes something less sinister and more elegant. It is an extreme solution to familiar equations, a place where mass, space, and time reveal their deepest relationships. The danger is not in their existence, but in misunderstanding their scale and behavior. By grounding black holes in real physics, something important happens. Fear loses its mystery. Awe remains, but it becomes informed awe, and that shift sets the stage for the real question ahead, not what black holes are, but whether one could ever realistically affect us at all. Now that fear has been replaced with facts, the question sharpens. Not whether black holes are scary, but whether one could ever realistically threaten Earth. To answer that, imagination must give way to probability, and drama must bow to distance, scale, and time. This is where most fears quietly collapse. For a black hole to endanger Earth, it would need to be extraordinarily close. Gravity does not care about labels, only mass and distance. A black hole far away is no more dangerous than any other object of the same mass at that distance. There is no hidden pull, no delayed attack. If a black hole were suddenly near Earth, its gravitational effects would be noticeable long before anything catastrophic occurred. Consider the nearest known black hole to our planet. It is more than 1,000 light-years away. That distance is so vast that its gravitational influence on Earth is effectively zero. Even if it were somehow moving toward us, which it is not, the timescales involved would be measured in millions of years. There would be no surprise, no sudden doom. What about rogue black holes drifting invisibly through space? This idea fuels many nightmares, but it collapses under scrutiny. Space is enormous, and black holes are rare. The odds of one passing close enough to disrupt the solar system are astronomically low. Lower than most everyday risks people accept without hesitation. The universe is big, but it is also sparse. There is also a common fear that the black hole at the center of our galaxy poses a threat. It does not. That supermassive black hole has existed for billions of years, and the Milky Way has remained stable the entire time. Stars orbit it peacefully at vast distances. Earth is 100,000 light-years away, completely unaffected by its presence. Another scenario often imagined is the Sun turning into a black hole. This is physically impossible. The Sun does not have enough mass to collapse into one. When it reaches the end of its life, it will become a red giant and eventually a white dwarf, gently shedding its outer layers. Earth may suffer then, but not because of a black hole. Even the idea of tiny black holes appearing near Earth, perhaps from exotic physics or particle experiments, has been thoroughly examined. If such microscopic black holes could exist, they would evaporate almost instantly. They would pose no danger, leaving behind nothing but equations and curiosity. Here is the crucial contrast. Black holes feel threatening because they represent extremes, but danger is not about extremes alone, it is about likelihood. Lightning is powerful but rare. The Sun is massive but distant. A black hole may be extreme, but it is also far away, uncommon, and predictable in its behavior. The universe does contain real threats, but they are slow, distant, and governed by warning signs. Black holes are not lurking monsters waiting to strike. They are quiet participants in cosmic structure, shaping galaxies over eons, not ambushing planets in silence. When probability replaces panic, the question answers itself. Yes, black holes can be destructive under the right conditions, but Earth does not live anywhere near those conditions. The danger exists in theory, not in practice. And that realization shifts the story from fear of annihilation to something more subtle, understanding our place in a universe that is far less hostile than it appears. That understanding prepares us for an even more revealing turn, because if black holes are not the great threat we imagine, it raises an uncomfortable possibility. Maybe the dangers we should worry about are far more familiar, far less exotic, and far easier to overlook. Once black holes are stripped of their cinematic menace, an uncomfortable contrast emerges. If these extreme objects are not quietly plotting Earth's destruction, then why does the fear linger so strongly? Part of the answer lies in how the human mind prioritizes threats. We are drawn to the dramatic and the unfamiliar, while far more realistic dangers fade into the background of normality. The universe is not short on hazards. It is simply indifferent to what we choose to fear. Asteroids, for example, have a proven track record. They have struck Earth before, reshaped the planet's climate, and altered the course of life itself. Unlike black holes, these objects regularly pass through our cosmic neighborhood. We track them, measure them, and occasionally watch them pass uncomfortably close. Yet they rarely inspire the same existential dread. Then there are stellar explosions. Supernovae release more energy in a moment than our sun will produce in its entire lifetime. If one were to occur close enough to Earth, the consequences could be severe, potentially stripping away atmospheric layers or disrupting ecosystems. These events are rare, but not hypothetical. They are observed, cataloged, and understood. The danger is real, but the fear is muted because the process feels abstract and distant in time. Even closer to home, the sun itself represents a far more immediate cosmic influence. Solar flares and coronal mass ejections can disrupt satellites, power grids, and communication systems. These are not science fiction scenarios. They have happened before and will happen again. Yet because the sun is familiar, life-giving, and ever-present, its destructive potential feels manageable, almost invisible. This contrast reveals something important about perception. We fear black holes not because they are likely to harm us, but because they violate intuition. They are invisible, final, and absolute. Asteroids, stars, and solar storms, by comparison, feel mechanical and predictable, even when their consequences are severe. Our brains mistake familiarity for safety. There is also a psychological comfort in fearing distant, uncontrollable threats. A black hole cannot be negotiated with, prevented, or easily imagined in everyday life. That makes it a perfect container for abstract anxiety. More realistic dangers, on the other hand, imply responsibility. If an asteroid is a threat, we might need to track it. If solar activity is dangerous, we might need to prepare. Fear shifts into action, and action demands effort. Cosmic dangers also unfold on timescales that do not match human instinct. Black holes evolve over millions or billions of years. Asteroids and solar events operate on timelines that overlap with human history. The mind prefers spectacle over subtlety, apocalypse over probability. As a result, we overestimate exotic risks and underestimate ordinary ones. Understanding this imbalance does not mean dismissing fear altogether. It means redirecting it. Fear becomes useful when it is aligned with evidence rather than imagination. The universe is not safe, but it is also not malicious. Its dangers are distributed unevenly, governed by physics rather than narrative drama. When black holes are removed from their role as ultimate villains, something more honest takes their place. A universe filled with processes that are powerful, neutral, and largely indifferent to human concerns. Some of those processes intersect with our lives, most do not. The challenge is learning which is which. This realization reframes the original question. The issue is not whether black holes are dangerous, but why our attention gravitates toward the wrong threats. By correcting that focus, we gain a clearer view of reality, one where wonder replaces paranoia and understanding replaces myth. And that shift prepares us for the final perspective, because even if black holes are not dangerous to Earth, they still matter profoundly to how we understand the universe and ourselves. If black holes are not lurking threats to Earth, if they are unlikely to ever touch our lives directly, then a final question remains. Why do they matter so much to us? Why do they occupy such a powerful place in science, culture, and imagination? The answer is not fear, but significance. Black holes matter because they sit at the boundary of what we know and what we are still trying to understand. Black holes are not important because they destroy, but because they reveal. They expose the limits of physics in a way few other objects can. Inside them, our best theories collide. General relativity describes gravity with stunning accuracy, while quantum mechanics governs the behavior of the smallest particles. In black holes, both must apply at once, and yet they refuse to fully agree. That tension is not a failure of science, but an invitation to go deeper. There is also a profound shift in perspective that black holes force upon us. They remind us that the universe does not revolve around human intuition. Space can bend, time can slow, cause and effect can behave in ways that feel deeply unnatural. Black holes challenge the assumption that reality must align with how we experience it. In doing so, they train us to think beyond comfort and beyond instinct. They also play a quiet but essential role in shaping the cosmos. Supermassive black holes sit at the centers of most galaxies, including our own. Far from destroying everything, they help regulate the growth of galaxies, influencing how stars form and how matter organizes itself over billions of years. They are not cosmic errors. They are structural features of the universe. On a human level, black holes capture attention because they embody extremes. They are places where density, gravity, and energy reach their limits. Humans have always been drawn to extremes, not because they are practical, but because they stretch imagination. Mountains, oceans, and storms once filled this role. Black holes now occupy that space on a cosmic scale. There is also something humbling about them. No matter how advanced our technology becomes, there are regions of the universe we cannot observe directly. Information can be permanently hidden. Knowledge has boundaries. Black holes confront us with the idea that mystery is not a temporary inconvenience, but a permanent feature of reality. This does not diminish science. It strengthens it. Science is not about eliminating mystery. It is about mapping where mystery begins. Black holes mark those edges clearly. They show us how much we have learned and how much remains unresolved. When fear is replaced with understanding, black holes transform from villains into teachers. They teach patience, humility, and curiosity. They remind us that the universe is not designed to be comfortable, but it is designed to be consistent. Its rules apply everywhere, even when they lead to outcomes that feel strange or unsettling. So are black holes dangerous to Earth? In any practical sense, no. But are they dangerous to our assumptions about reality? Absolutely. They force us to question what we think we know about space, time, and existence itself. And that is not a threat. That is the engine of discovery. In the end, black holes matter not because they might one day reach us, but because they already have, not through gravity, but through thought. They cull our curiosity, bend our understanding, and quietly remind us that the universe is far larger, deeper, and more surprising than fear ever suggested.